A car is designed to be stable. We know that the stability is linked with the center of mass and base area. Larger the base area, greater would be the stability. Similarly, lower the center of mass, more the stable an object would be. So let's see which option is possible. Okay, to achieve good stability, where is the center of mass? Center of mass should be lower, as lower as possible. Above the front wheel, oh no. Above the rear wheel, that's also not possible. As high as possible, that's totally wrong. As low as in the car as possible, yes, that looks fine, because as low as it would be, the more stable the car would be. A man uses, next number 8, a man uses clay to make a pot. He wants the pot to be as possible, to be as stable as possible when placed on flat surface. Okay, so for stability, again we need two things: large base area, lower center of mass. Which two features of the pot must the man consider? So two features are very common. Like two features are well understood. The first thing is larger the base area. Second is lower the center of mass. The area of base, okay, base area should be high. Okay, the height of the center of gravity, the density of the clay, and area of the base. Area of base matters. Like area of base matters, density doesn't matter. So let's consider few things. Density doesn't matter. Okay, it matters. The density of the clay, the density of the clay and height of center of mass, it doesn't matter. It matters. The weight and height of center, the weight, there is no link of weight. So that's wrong. So one part is wrong means totally wrong. So we have option A, the area of the base, like larger the base area and lower the center of mass. So we are actually in need of this one. It has both possibilities, so we are going to consider this option. This is our correct option. Number 9, what affects the stability of an object? Like again, the base area and the center of mass or center of gravity. Only its weight. No, weight has no. Only the location of center of mass. No, base area also matters. Only its weight and base area. There is no link of weight. So we are actually in need of base area and center of mass. So that's why the stability is linked with the base area and center of mass. This is our possible option. Number 10. Which chair is the least stable if the child moves? Okay. Now again we are going to apply the both possibilities, the base area and height of center of mass. Suppose like this is the center of mass in a boy. Suppose here is center of mass. Suppose again here is center of mass. Here is center of mass. So the conditions are the base areas. You can see it has small base area. It also have small base area. So these two options are totally rejected. Oh, 1 second. Like the question is about least table. Least table. So least table means small base area. The one with small base area would be least table. So it means this one is not stable. This one is not. This one is stable. Looks stable because its area is large. Base area is large, so it looks stable. And the question is about least table. Least tables are those which have small base area. So A and B both have small base area. So these two are possibly unstable. So with respect to area, base area out of these four. Now, second thing is their center of mass or center of gravity. So it has lower center of mass or center of gravity. So it looks comparatively more stable than A. And the center of gravity for A is little high. So it is less stable and this one is more stable. So comparatively, this one is more stable. That's why we are not going to consider this. We are going to consider this because it is least stable and the question is about least stability. So the option A is correct because in A, the boy is a child is more unstable or least stable. A piece of uniform cord is suspended freely from a horizontal pin like this. This is a pin where the particle, this uniform cord is suspended. Which point is the center of mass? Okay. Like A is center of mass, B is center of mass, C is center of mass, D is center of mass. And most probably the center of mass is C because it is lower. And you can see if we find out, there is a method to find out the center of mass. Suppose we insert a pin here, then expectedly it would go something like this. We can expect something like this. Then again, we can use here, it can go similarly like this. And here is when pin is here, so it looks little central part of like kind of the part where whole weight would be concerned. So that's why we can consider C would be our better option. Now let's move to number 12. In 12, two stretch spring X and Y are attached to the end of the meter rule. Like here is a meter rule and we have two stretch springs like this as shown in figure. A weight of W is here is hung from one end. Here is a pivot point. A pivot is the center of the rule. Is the center of the rule. Okay. The weight W is moved towards the pivot. Okay, if you move this weight to here, like this weight is actually here. If you move it somewhere here and somewhere here, then here and here. How does the tension of spring changes? Okay, so we can assume that uh, like suppose let's assume that weight is 100. Suppose weight is 100 and this distance is also 100. Okay, okay, so if the weight is here, weight would come here, here, here. Weight is not going to change along this one. But if the object is here and if we move it here, the distance will decrease. Perpendicular distance decreases means anti-clockwise movement will decrease. You can see that this weight is actually responsible for anti-clockwise movement. Yes, anti-clockwise movement. This weight is responsible for anti-clockwise movement. If we move this weight from this position to here, you can see that anti-clockwise movement from this side starts decreasing because distance is decreasing. If you further move here, the anti-clockwise movement decreases, and so on. So when anti-clockwise movement decreases by moving the weight to the right side, similarly, this spring is actually responsible for a counter, like anti, this spring is actually pulling the rod, meter rule, to for clockwise movement. Then what will happen is, okay, as long as the weight is here, when we hung weight here, what will happen, the situation would be something like this. If I can draw it, we will have pivot, like this rod would become something like this, because the weight is actually creating a anti-clockwise movement on the left hand side. And now you can see when the rod will move in upward direction, the x will be compressed and y will have extension in it. So the situation would be, if I can draw it, this would be the situation. And on the upper side, the situation would be something like this. The upper part, x part, would be little compressed, and the lower part, which is y, it would have little extension in it. Okay, now we were talking about when the weight is moved towards the right. As we move, like as we start moving the weight towards the right, the movement clockwise, that is anti-clockwise movement starts decreasing, and this would become something like this. Its situation starts changing, like it would become something like this, and it starts getting flat and flat and flat. Now this is the situation. As we move to the right, the ruler would start become flat and flat, and that would make this x1 to get little like initially it is compressed, but once it moves it to the right side, the x starts gaining extension, and the y starts getting compression like this. So there would be a decrease in y as we move towards the right, and there would be an increase in x as we move towards the right side. So conclusion is that the x1 will get extension, means it's and it starts getting compressed, so its tension decreases or its extension starts decreasing. So the possible option is x increases. So x increases here and here, and y is decreasing. Y decreases here and y decreases here. Rest of the options are incorrect. So our option is this one. Number 13. A beam pivoted at one end. This end is pivoted, means fixed end. Has a force of 5 Newton. Here is a 5 Newton force. Here is a 5 Newton force which is acting in upward direction, vertically upward as you figure. The beam is in equilibrium. The beam is in equilibrium. Okay. What is the weight of the beam? Okay. We know that. Let's calculate the movement generated by the beam, generated in the beam. So clockwise movement and anti-clockwise movements are equal. So clockwise movement is generated by weight. So this weight is responsible for clockwise movement. Here is clockwise movement in it. And this one is responsible for anti-clockwise movement. Okay, for clockwise movement, we have force, which is weight. We don't know about it. And the length is 3 centimeter plus 2 centimeter. This is 5 centimeters. And on the left hand, what about anti-clockwise movement? For anti-clockwise movement, we have 5 Newton force, and 5 Newton is at 2 meter distance. Okay. So we can see 5 is cancelled with 5. So weight is 2 newtons.